Hi, I'm Maurice Temer, and this is a joint work with Haim Kaplan, Yishay Mansour, and Kobbi Nissim. And the one-line summary of what I want to tell you is that we present a new security definition for preventing reconstruction attacks based on leveraging or arguing about the attacker's knowledge, and we give an example for when this definition is useful. So let me start with this motivating slide. Why should we even care about or study protections that are limited to one type of an attack, like a reconstruction attack? Because this is obviously not good enough in general for protecting privacy. So I guess that there are three answers that I could give you. The first answer is that, we or the community have been studying and talking about this concept of reconstruction for basically more than 20 years. And I think it's important to try and understand this concept better and try to understand when can we prevent reconstruction from happening. The second reason is that, many real-world deployments of differential privacy use very large privacy parameters, and I think it's important to try and understand what does this give us. Is it the case that these deployments still give us some protection, maybe in the form of protecting against reconstruction attack? We want to understand this. And the third reason is that, maybe, and that's a big maybe, but maybe there are still cases where providing these kinds of weak protections, let's say protect only against the reconstruction attack, maybe there are cases where this suffices. Okay. So let's see how prior works approach this concept of trying to define what does it mean to prevent against reconstruction attacks. And as an example, let's think about a dataset S that contains images, and then there is a mechanism M that operates on this dataset and returns a release Y, which in this example, let's think about it as an image model. And then there is an algorithm A that takes this release Y and tries to reconstruct S or some portion of S or some row of S or some collection of rows from S. And the output of A, the candidate reconstruction that it outputs, we will call it Z. Now, intuitively, we can say that M prevents reconstruction if this Y is hard to invert in the sense that A cannot recover non-trivial data from S. Okay, that's intuitive enough, but what does it mean to recover, and what does it mean to be non-trivial, right? So regarding the first question here, regarding what is recover, we are not going to answer this question, and like basically all prior works on this topic, we're going to abstract this away in the form of a relation R, such that R applied to the dataset S and to the candidate reconstruction Z tells us whether or not Z is a valid reconstruction of the dataset S. A simple example to keep in mind is simply the relation that evaluates to 1 if and only if Z belongs to S. In the paper, we consider other types of relations as well, but for this talk, that's a good example to keep in mind. The reason for this abstraction via the predicate R is that the notion of successful recovery seems to be very context dependent. For example, I guess that the criteria for when is one text file a successful recovery for another text file would be very different from the criteria for when one image successfully recovers another image, right? Okay, so that's fine. We introduced this reconstruction relation R. I guess this is some answer to the first question, but we still need to understand what does non-trivial mean, right? Intuitively, we want to say that for the attacker to succeed in its attack, it should recover something that could not be recovered without Y. Here is an example illustrating this. Suppose that the attacker knows that every image dataset, or every large enough image dataset, contains the Mona Lisa, and then the attacker sees Y and says, aha, you had the Mona Lisa in your dataset. Okay, so the attacker is correct. We had the Mona Lisa in our dataset, but that's not a very impressive attack, right? Because the attacker knew this before even seeing the release Y. Okay, so we're going to follow the treatment of Cohen et al. For formalizing this example. They proposed the following security definition, which they call Narcissus resiliency, saying the following. Algorithm M is secure, Narcissus resilient, with respect to the data distribution D and with respect to the reconstruction relation R, if the following holds. So we have here two experiments. In the left experiment, we sample the dataset S from the underlying distribution D, we run M on S to get the release Y, and then that we run the attacker on the release Y to get the candidate reconstruction Z. And then we test whether or not this C is a valid reconstruction with respect to S. On the right experiment, the same thing is going on, except that at the end of the day, we test Z not with respect to the actual dataset that M was executed on, but instead we test Z with respect to a fresh dataset T that is independent of Y. And now the security definition says that whatever A is doing, whatever strategy it is using, the probability of a successful reconstruction with respect to S should not be much larger than with respect to the fresh dataset T. So intuitively, if M is secure, then the attacker cannot achieve non-trivial reconstruction because whatever it reconstructs is also a reconstruction with respect to the fresh dataset, and we consider this to be trivial. Okay. So here I just copied the definition of Narcissus resiliency, and now once we have this definition, we can ask if there are cases where this definition actually helps us in the sense that we could satisfy it while getting improved utility compared to what we can get or what we know we can get while satisfying differential privacy, right? Okay, so the first answer, and it's not a very interesting answer, is that yes, because Cohen et al. Showed that for counting bits, under some assumptions on the underlying distribution D, then you could count bits deterministically while satisfying this definition of Narcissus resiliency. So what it means is that for the task of counting bits, there is a mechanism that is Narcissus resilient, but this mechanism cannot be differentially private because we all know that for differential privacy, you cannot be deterministic. So that's an answer, but it's not a very interesting answer, right? Because, yeah, we cannot count bits deterministically while satisfying differential privacy, but nevertheless, we can count bits very efficiently with very small error while satisfying differential privacy. So we can count bits with differential privacy. So I guess that the real question here is if there exists a task which we can solve much better while satisfying Narcissus resiliency compared to when satisfying differential privacy. And the answer to that question is that currently we don't know of such a task. So I guess that maybe this means that we want to further relax this security definition of Narcissus resiliency in order to support even more utility. And essentially that's what we are doing in the current paper. The main conceptual modification we introduce in this paper is that we take or want to take into account the attacker's knowledge. To motivate this, let's consider the following example. Suppose that the underlying distribution D is uniform over some large domain, and then S contains n samples from this distribution. Now suppose that the mechanism M takes S and releases the hash value of every point in S for some hash function. Now, for an appropriate choice of this hash function, you could easily show that no attacker, even unbounded, no attacker can reconstruct points from S from this release, and you can actually even show that this mechanism satisfies the definition of Narcissus resiliency. Okay, so that's fine, but what about attackers with side information? For example, what if the attacker already knows a small superset, nice S, that contains all of the sample S, and then this attacker gets to see the release, all of the hash values of points from S. So in that case, such an informed attacker could easily identify all of the points in S from the release and from its side information, right? Okay, but that does not really feel like reconstruction, right? Because intuitively, at least, the attacker in this example reconstructed the dataset S mainly from its side information and not so much from the release Y. I guess that an alternative way to say that is that we cannot hope to protect against an attacker reconstructing a point from our sample if this attacker already knows that the point was in the sample. I mean, this motivates us to try and quantify the amount of side information that the attacker has on the sample S. That's all I'm saying. But actually, we argue in this paper that it's not enough for us to talk about the side information that the attacker has on S, and we actually also want to talk about the amount of side information that the attacker has on the underlying distribution. So here is a tweak to the previous example that illustrates this, and I'll come back to this example number 2 later on. So now the data distribution D is itself generated at random by first sampling the superset nice S, and then defining D to be, let's say, the uniform distribution over points from this superset nice S. So nothing changed really, right? I mean, if the attacker knows the superset and sees the release, which is the hash value of all of the points in the set S, then this attacker could still, just like before, identify all of the points in the sample S. Okay, but I guess that a conceptual modification here is that now this superset is part of the distribution D. So now the attacker's knowledge is more about the distribution rather than about the sample. So the takeaway from this example is that we want to be able to argue about the knowledge, or maybe the lack of knowledge, that the attacker has about both the dataset and the underlying distribution. In our paper, we model this via a Bayesian perspective by considering a meta-distribution, we call it prior, where the underlying distribution D is sampled from this meta-distribution prior. This way, we have that both the data distribution D and the sample S are random elements, and this allows us to argue about the lack of knowledge that the attacker has about them. So here is a statement of our results. First, like I guess I already said, we introduce a Bayesian analog for Narcissus resiliency, and I'll show this to you in the next slide. And then what we do is we show that our definition has implications to the marginals problem, which is a notoriously hard problem in the literature of differential privacy. And here is the definition of this marginal problem. The definition of this problem is very simple. We get n vectors in d dimensions, n binary vectors in d dimensions, and our goal is to approximate the average of these vectors. What Ban, Ullman, and Vadan showed is that this problem is unsolvable with differential privacy unless n is at least root d. And specifically, what they showed is they presented a hard instance for this problem that forces every differentially private algorithm to fail. again, unless n is at least root d. What we show is that this hard instance can actually be solved while satisfying our new security definition, even when n is much, much smaller than root d. And I guess that, as far as we know, this is the first formal security notion of any kind for this hard instance. Okay, so here is a simple variant of our new definition. And in this simple variant, the only modification we make compared to the definition of Narcissus resiliency is that in both experiments, the data distribution D is first sampled from the meta distribution prior, and then everything continues the same. So let's read this definition together. A mechanism M is, we call this definition Bayesian extraction safe with respect to a meta distribution prior and with respect to a reconstruction relation R, if the following holds. Suppose that we sample the data distribution D from prior and then sample a data set S from D and then run algorithm M on S to obtain a release Y, and then this Y is given to the attacker, then algorithm M is Bayesian extraction safe if the probability that the attacker succeeds in reconstructing with respect to S is not much larger than the probability of it succeeding to reconstruct with respect to the fresh sample D. And I'll just mention here that this is not the final definition in our paper, because this definition does not yet allow us to take into account additional side information that the attacker might have. But I'm not going to talk about it here. So you could either see the paper if you're interested, or come see me and talk about it at the conference. And actually, it's kind of even subtle to explain why do we even need to explicitly incorporate additional side information beyond this prior. I mean, why can't we just take into account the side information in terms of this prior? But again, you have to see me at the conference if you're interested, or look at the paper. Okay, so let's see what does this new definition gives us with respect to the marginals problem. So again, the problem is to approximate the average of n binary vectors in d dimensions. And as we mentioned, Ban, Ullman, and Vadan showed that this problem is unsolvable with differential privacy unless n is at least root d. And to show this, they presented a hard instance, which in our terminology could be thought of as a meta distribution. So the hard instance is a meta distribution, which we will call hard prior. And this hard prior has the following structure. When sampling a distribution from this hard prior, we first sample a superset containing binary vectors according to some special distribution on this superset. And then the target distribution is defined to be uniform, let's say uniform over this superset. So this is actually somewhat similar to example number 2 from before, right? Anyways, what Ban, Ullman, and Vadan showed is that differentially private algorithms cannot solve the marginal problem over datasets sampled like this. Okay. What we do is we revisit the same hard instance, under our new definition of Bayesian extraction safety, and we conduct some sort of a case study according to the side information available to the attacker. So first, what we show is that if the attacker does not have any side information, and in particular, this means that the attacker does not know the superset defining the data distribution, then in that case, even the exact average is secure, in the sense that the mechanism that takes n binary vectors returns their exact empirical average. That mechanism is secure according to our new definition, even when n is much, much smaller than root d. Second, we show that if the attacker does have side information, then the exact average is no longer secure, and the attacker could reconstruct basically all of S after seeing the exact average, the release. And finally, we show that we can still satisfy our security definition even when the attacker has side information and still keep N very, very small. But now the mechanism is different, some version of noisy average. Okay, so the summary of what I presented here is that we introduce a new Bayesian perspective on the concept of data reconstruction. We leverage this new perspective to propose a new security definition that relaxes the prior definition of Narcissus resiliency by arguing about the attacker's knowledge. We conduct, as I said, a case study regarding our new definition with respect to the marginals problem under different assumptions on the attacker. And finally, this is something that I didn't mention here in the talk. Our work has implications to the literature on data memorization, but again, I didn't talk about it here. So that's it. Thanks for listening.